Okay, welcome. We're now going to go through the work solutions to Dynamics Worksheet 4C, 4, which is power, force, and average speed. This is the worksheet that goes with the formulas that we just went through, saying that power is equal to force times a constant velocity. So we use this formula when a force is acting, and because of friction, we have constant velocity happening. Okay, so starting at question 1 here, we've got a person pushing an 8-kilogram box along the floor with a force of 50 newtons, and the box is moving at a constant speed of 2.5 meters per second. So the question is, what is evidence is the floor is applying a frictional force? And we know from our discussion of Newton's second law that force equals mass times acceleration. So a force acting must create acceleration. If I have a force acting and it doesn't have acceleration, in fact, this time it is constant velocity of 2.5, then this force here must be balanced with a backward force there. It must be the net force must equal 0. So I have evidence that there is frictional force because if I'm pushing with 50 newtons, I should get an acceleration in proportion to that. But because I'm getting only constant velocity, we must have friction acting against it. So that is 1A. That's the evidence. So we're going to calculate the expected acceleration. So this question is all about understanding or trying to work out why we have to use this formula. So if we were to just apply Newton's second law, we should get a 50 Newton force pushing an 8-kilogram box, and it should produce that acceleration there, which is 50 divided by 8. Oops, 50 divided by 8. I should have done that in my head. That's 6.25 meters per second squared. That should be the acceleration. The frictional force, because it is not giving that acceleration, it's actually giving an acceleration of 0 because there is no velocity, then the frictional force must equal the forward force, which is 50 newtons, in the opposite direction. Okay, so this would be in the opposite direction to capital F there. Now calculating the amount of power using D, because we have a non-accelerated motion and our velocity is not changing, in other words, friction equals our forward force, we use the formula P equals F parallel to V. Now in this case here, it is always parallel because our box is being pushed this way and our velocity is in the same direction. This is very handy when it's like being pushed on a floor or something like that. Pushing a pram or pushing a mower where you are pushing down a handle or pulling up from a handle, that would require us to take F and resolve it into its components. So in this case, it's a very simple process that the driving force here is 50 newtons, and that 50 newtons is producing a constant velocity of 2.5. So 50 times 2.5 will give us 125 joules per second or watts. Okay, but yeah, so let's try another one now where we're not pushing in the same direction. Question 2 has Jenny pushing a mower. Okay, so here she's pushing down that handle and the mower will be going forward. That's parallel to the earth, but the force is not parallel to the direction of the velocity. In this case, we have to find the component of the force that is pushing it forward. So looking at the question 2, here is the force going down there on the mower. That's 30 newtons. And it's going forward at the velocity of 0.8 meters per second, very similar example to the one that I put on the larger video. And this angle here is 65 degrees. Okay. Because this velocity vector and the force vector are not in parallel, we have to find the part of this force that is parallel. So this force here will be resolved into two sections. This one going down here is obviously not parallel to V, so we're not going to calculate it. We are just going to do the one that is parallel, which is that one. Most of the time, this will be close to the angle, so it's going to be the cos vector. So it's 30 cos 65. And that's reflected in the formula that I have placed over here, that is cos. Please don't always assume a cos. I just put that here because most of these here have a cos. It depends on which angle is given. In this case, it is the vector down here, which is close to the point of motion. Rightio, so the power generated by good old Jenny here is equal to force, which is parallel to the velocity, which is 30 cos 65 times 0.8. Calculating that, that's 30 cos 65 times 0.8, and that's 10.1 watts, 1.4 to be exact, but let's quibble. Okay. How much work does she do? Now, work, remembering the work relationship to power is work over time, like that. So if we, even though this formula doesn't have any time in it, we can revert, remembering we are calculating power. So this power and that power are the same thing. And that means that we can now work out what our work is, because work would equal power times time. And that would be 10 point, I might use the exact value that I had last time, or not the exact, but the more accurate value, 10.14 times the time, which is, we are told to do it for 15 seconds. And so multiplying that by 15, it's 152.14 joules. Okay. So that's how much work has been extended. Okay. The next part is to outline the following terms in relationship to a car. You can find this information in your textbook, and just find that little section after this section. You'll find the reference to the pages in the description on Compass. Moving on to question 4. Question 4, a car has a mass of 1,200 kilograms and is traveling at a constant speed of 16 meters per second. Now, when we are doing a car, so here's our car. Just go through, wait for the bell. Okay, when we're doing a car, obviously a car, I'll just do a box car. There we are. A car, its driving force is that direction, and it would be the velocity would be parallel. So in this case here, the forces are in the same direction. Okay, so we are not going to have to worry about resolving the final forces. And the mass of that car is equal to 1,200 kilograms, and the constant velocity is 16 meters per second. Okay. The rolling resistances we are told that the combined rolling resistance of the car, all the retarding forces, add up to 650 newtons. So this is all the friction forces on the way back here are 650 newtons. However, we've got a constant velocity going forward, so what do I know must be the forward force? Well, that forward force must also be 650 newtons, okay? Because otherwise we wouldn't get this constant velocity here, okay? If this force here was not 650 newtons, it was less, then the friction is bigger than the forward, and the car will start to slow. If this is more, then this wouldn't be a constant velocity. This would start to accelerate until the air resistance and the rolling resistance once again makes these two values equal. Right, so now we've got the F. Remember, power is equal to F parallel to V. We need that, and we just need that value there. Okay, so all we've got to do is shove in the numbers. That's 650 is the forward thing, and the velocity is 16 meters per second. Okay, you can simply do that calculation yourself there. Okay, so that's question 4. Moving on to question 5. A car is traveling at a constant velocity of 80 kilometers per hour. The combined resistance of the car goes to 180. Calculate the power supplied to 3 significant figures. I'm not going to do this one for you because it's identical to question 4. The only trick here is that your velocity is given in kilometers per hour, and you need to convert that to meters per second. Moving on to question 6. A crane is lifting a 200 kilogram mass at a constant velocity for 12 seconds. Now this time the actual motion, so in question 6, the crane is lifting it that direction at a constant velocity. So there is a force, a lifting force there. And this means that we haven't got friction this time, but what would be the force that is pulling it down and making it equal? That would be the weight force. Okay, so this is the crane's lifting force, and this would be the weight force. So going back to the question one more time. Oops, there it is. A crane is lifting a 200 kilogram mass at a constant velocity of 2.8 meters per second, and it's happening for 12 seconds. Right. So we know that this lifting force must be equal to, if it's a constant velocity, must be equal to the retarding force. In this case, the retarding force here, the force that's pulling against the actual driving force, if you want to call it that, it's the lifting force, would be weight. So let's calculate the weight. mg is equal to 200 times 9.8. So 200 times 9.8 is 1960 newtons. So 1960 newtons is pulling down there. So if this crane needs to lift this box, then it must be giving the same amount there. So this must equal 1960 newtons there. Okay. If the crane is higher than 1960, what would happen to this mass? This mass would accelerate upward. We are told that it's not accelerating upward. It is coming up as a constant velocity in the upward direction of 2.8 meters per second, which is quite fast actually for a crane anyway. So if it was that the crane was less than this number, then the crane would not be lifting because the weight of the box or the load would be too big for the crane, and this would be bigger. So when these two forces are in balance, we get a constant upward velocity. If this was bigger, we would have acceleration upward. So just careful of what's going on here. It's in the vertical. We don't have, in this case here, we're not having friction, we're having weight as our retarding force. Right, so the question is for A, what is the minimum power? Well, the minimum power would happen when it is actually at that force there. Anything less than that, we don't get any motion or upward motion, we get downward motion. So power would equal F parallel to V, and the F in the upward direction, which makes it parallel to V, is 1960 times 2.8, and multiply that 2 by 8, we get 5488 newtons. Okay, so don't get yourself too overly worried about this word minimum in this position here. That's just being very technical to make sure that we are actually moving this thing upward. To work out the work, we revert to the other formula for power. Power is work over time, and therefore work would equal power times time. We know the power. Oops, I put newtons over there for that power. Yeah, we just change that. If you have already written that down as newtons, that's meant to be watts over there. So the power is 5488 watts, and we need a time, and the time is given in the question as 12 seconds. Okay, so that's times 12, and so multiply that by 12, and this is the amount of joules. That's 65856 joules is needed for that motion. Okay, or for that to these criterions to be met. How far did the mass move during this time? Well, we have a constant velocity here. So therefore, it's unaccelerated motion. In that case, we can use V equals S on T because that's the formula for unaccelerated motion. Velocity is distance over time as long as there's no acceleration. We can use this one. If there is acceleration, we have three equations of motion that we have to use. So how far did it go? S equals Vt, and so the velocity is 2.8 times 12. So it's 2.8 times 12, and that is 33.6 meters in the vertical. Oops, moving that up a bit. There. Okay. And the final question is, what is the sum of all the retarding forces? Well, the sum of all the retarding forces, in this case here, is 1960. Okay. This would be mg is the weight. That's the major retarding force. But obviously, as it does move up, there will be air resistance as well as it goes up. And even the crane would have internal resistances. Okay. And the final question is Jeff running up a flight of stairs. Here, the velocity, he's going up at a constant velocity in this direction. So I'll leave this one to you to have a go and see if you can, because it will lead you through the answers to this one. I will necessary if you just email me and say you do need question 7. I want to have this as a one which I'm not going to give you help through to see how you can go getting this. Okay, enjoy.